This next type of problem is an awesome review of a few things that we've done throughout the whole semester. We're going to use molar masses, which we learned about in chapter 4. That is, remember, grams per mole, and we get that from the periodic table, those masses there. We're also going to use mole ratios, which we learned about in chapter 6. And then we're also going to do the ideal gas law, which of course we're learning about right now in chapter 9. Mole ratios, remember, are moles of A over moles of B, and those mole ratios we find in balanced equations. So we will be using balanced equations in these problems that we're going to work on now. The ideal gas law is PV equals nRT, and this is going to be the new piece that we have not ever combined with stoichiometry, mole ratios, or molar mass before. So I just want to help you remember the different things we've learned so far, and we're actually going to add a few things on in chapter 11 and 13 to this as well. So in the past, in chapter 6, we had figured out that if you have grams of sodium azide, we could convert that to moles of this sodium azide, which is very explosive. It blows up then into a gas. That's usually what explosives do, is go from solid to a gas. So I can convert grams to moles, and then I can use mole ratios, and I could say, well, hey, I really want to know about sodium, so then I could also convert this back to moles of sodium, or go all the way to grams of sodium. Or say I'm more interested in how much gas I'm going to get if I'm like building an airbag. This was an old original airbag reaction. Then I could work my way over here and say, now let's find out the moles of N2, or maybe you want to know the grams of N2. So we have a new addition to this, and this allowed me to go any which direction, right? The mole ratio was kind of the hinge to get from one chemical to the other, and then I can use molar masses between all these grams and moles. So the new piece is, often with gases, I don't really want to know the grams of gas, I want to know the volume of gas. So if I want to know instead what the volume of N2 is, then now I have a way to get from moles to volume, and that's the ideal gas law, right? Here's my moles, and here's my volume. I could also go to pressure or temperature, but volume's the most common one. And so to get between moles and volume, I can use the ideal gas law. So it's still stoichiometry, which is like half of what this class is ultimately, and a lot of what you'll see in Chem 1A. It's just a new connection point, and then I can still work my way into the mole ratios and back to any other substance in the equation. So we're going to use that in a big stoichiometry problem on the next page. So same conversion tools are available to us. Note that given in these problems should be the reaction conditions, which are standard temperature and pressure, or STP is how you'll see that abbreviated sometimes. And STP is 1 atmosphere and 273 Kelvin. So standard pressure at sea level, and then a temperature we never see, which is 0 degrees here in Long Beach. But 273 is considered our standard temperature. So we're going to look at this as if it was airbags, or look at these types of problems. So if we have a typical passenger airbag in a car and it has 250 grams of the explosive, the sodium azide in it, the question is, what is the volume of N2? So right off the bat, I can tell this is going to be a stoichiometry problem because I see sodium azide and N2. And so if I switch chemicals somewhere in the problem, I'm going to have a mole ratio. Now, I also have a couple of other givens. That's these reaction conditions here. So I know what the pressure is. It's going to be 1 atmosphere, and I know what the temperature is, 273 Kelvin. But these are all going to be together for my N2 gas. And I actually am starting here with a mass of something else. So if you can kind of picture it, and a plan often helps on these, I can go from my grams of sodium azide to the moles of sodium azide, and then to moles of N2, and then to a volume of N2. And that moles to volume piece is the new piece that we saw on the last slide. That is where I'm going to use my ideal gas law. So if I can look back here, I'm given grams I'm going to convert to get to the mole ratios, and then come over here, moles to that final volume. So that's kind of the path that I'm going to take here. So let's start with this 250 grams. That's the only number that's given, so I have to do something with it. 250 grams of sodium azide, and I have in my head I need to get to N2. So first I'm going to follow my units down, grams of NaN3. I want to switch to moles, so I can use this mole ratio. Moles of NaN3. So I go to the periodic table, this is a molar mass, right? And add up a sodium and 3 nitrogens, which gives me 65.02 grams. Molar masses are always per 1 mole, don't forget that. And then I want to get to this N2. So follow your units, moles of NaN3, and I can convert that to moles of N2. Notice there I'm going to stop so that I can do my ideal gas law, so don't go all the way to grams. And the numbers I'm going to plug in here are going to be the coefficients, so 2 moles of NaN3 to 3 moles of N2. So now I've gone from my solid to my gas, and then I'll do a volume conversion next. The number that I get here, 5.767 moles of N2, because my other units cancel out. Only 3 of those digits are significant. I'm just keeping an extra one so I don't round too much. So now I'm going to solve for V. So let me come over here, PV equals nRT. If I want V is going to be nRT over P. So that's what I want to plug in here. So the moles I just figured out, 5.767 with 3 sig figs moles times the gas constant, 0.08206 liter atmospheres, mole Kelvin, divided by, times temperature, which was 273 Kelvin, and pressure, 1 atmosphere. We can assume that these are exact numbers, so they're not going to impact our significant figures, the standard temperature and pressure. So when I go to calculate this, make sure your units cancel. Got everything set up right. So my liters aren't going to go anywhere. My moles, numerator, denominator, Kelvin, numerator, denominator, atmospheres, atmospheres. When I do this, I get 129 liters of N2. And that's a huge volume, which makes sense. If you're thinking airbag, it should have a huge volume. And so that is going from my original mass of explosive to how many moles of gas, and then I take the moles of gas and I figure out the volume of gas. You have another problem here, which we'll save and work on together, or you can try it ahead of time. This was the passenger airbag, and I don't know if you know this, I've never experienced this firsthand, but passenger airbags are bigger than driver's side airbags. So a driver's side airbag, you only need maybe say 56 liters of nitrogen in a smaller car probably. So then I can work backwards to figure out how many grams of sodium azide I need. Again, assume that we're at that standard temperature and pressure. So I've got this volume and I'm going to work backwards to the sodium azide. Just a little hint here. If I know liters and I want to get to here, the grams of sodium azide, I'm going to have to convert to moles of N2, ideal gas law, and then mole ratio, and then back to grams. So I'm doing exactly the opposite of what I did last problem. So I will leave you with that to practice, and there's more of these in your workbook to practice as well.